So the question says, calculate the equilibrium concentration for all the reactants and products if 0.500 moles of ICL is placed into a 5.00 liter flask with KCl equals 0.110. Okay, so what is the first thing that we want to do? What would be the, well, of course, other than making sure our equation is balanced, what would be the thing that we want to do in this circumstance? Selena.
Hello.
Hello, can you hear me?
Yes, I can.
Okay, so what is going to be the first thing that we want to do?
Would we write down what we're given?
Okay, so let's write down what we're given. So we have 0.500 moles of ICL and 5 liters in a 5-liter flask. We know that this is a gas, so what can we calculate with this? The moles and the liters.
Would that be the molarity?
Molarity, that's right. So we know that molarity equals moles over liters. And so in this case, we have, or 0.500 over 5.00 liters. So we get the molarity is 0.100 molar. Okay, so this would be the concentration of what?
Would that be the concentration of the reactant?
That's right. So this is our IC, our concentration of ICL. Okay, so what else? So this is going to be what it's starting out with. It's going to be our starting concentration. So how would I calculate the concentration of everything at equilibrium? What am I going to use? So what do we know? What else is given to us? We have this. What is this?
KC.
Okay, what does that stand for? Obviously, it's the KC.
I honestly don't remember, but I think it does have to do with concentration.
Sort of, yes. It does have to do with concentration, yes. Anybody want to help her out? Gracia, what does the KC stand for? What is it representing?
Is it the equilibrium constant?
It is the equilibrium constant. Okay, so we know that it's the equilibrium constant. What do we know about the equilibrium constant? Can we use that for anything?
I have a question, Dr. Henry.
Yes, I may have an answer for you.
Is KC the ratio?
Ratio of what? That's sounding good.
The ratio of equilibrium.
Okay, so
Of the,
so we can say KC
yeah,
is
that's my
equal
question. If KC is like a ratio
okay.
for equilibrium.
Okay, yes, I will say definitely it is. So what is it going to be equal to if it's going to be this ratio?
Would it be your products over your reactants?
That's right. It's going to be the concentration of my products over my reactants. But we know it has to be to what power in terms of the reactant?
The second.
That's right, because the coefficients we're going to use as our power. Okay, so this helps us out. So we know what the equilibrium constant is. We know what our starting concentration is. So if we have our initial concentration, what else do we need to do to sit there and get the concentrations at equilibrium? Ice, baby.
The ice table.
The ice table. Okay, so we're going to be using that ice table. So what does ice stand for?
Is the I initial?
I is initial, okay? So we only have one initial concentration. That's this guy over here. So we're going to put that guy in there. And we know that everything else initially is going to be 0. Okay. The C, what does the C stand for? In every season, dun, dun, dun. Change. Okay, so C represents change. So the change that we're getting. So in this case, this guy's going to be minus X. These guys are going to be X. So equilibrium is going to be the sum of the initial minus the change, or the sum of the initial and the change. Okay, so then we can use this and plug it into our beautiful equation here. Okay, so we're going to make a quick assumption just for quick calculations and to see how, how well we're doing. We're going to make the assumption that this X value is going to be so small that it's going to have very little effect on the change of this. And this kind of gives us an idea of, our ballpark numbers. And then we'll go ahead and do it the long way. I forgot one thing to give you guys. Let me do this real quick before I forget. If I can find it. Give me a second. Let's see. No. Of course, when I'm looking for stuff, I can never find it. No. There we go. Okay. So I'm going to give you guys this link for the quadratic equation to kind of save us a little bit of time. And you guys will have this available on the exam. Can you guys see my screen?
Yes.
Yeah.
Okay. And if I can find what I'm looking for, make it easy, right? There we go. So I put it in the chat window. So mark that. It works. It'll send you to another link later on. They're trying to sell stuff to me. So, but it works really well. Okay, so now back to our problem. So if we go in through, and actually let's start with the hard way and then we'll do the easy way. Hard way, we'll go ahead and use the quadratic formula on this problem. So we'll go ahead and plug in the numbers. So we have Kc equals 0.110. If we go ahead and solve this equation, we have x squared equals 0.110 times 0.100 minus x squared. So we get x squared equals 0.110 0.0 minus 2, 0.100x. And you guys are going to let me go ahead and make that big mistake right there. Minus 0.100x plus x squared. So we get x squared Okay, so then we bring it all on this side of the equation. So we'll get (0.89) x squared plus 0.022x minus 0.0011 equals 0. Okay, so we can use the quadratic formula. So if you guys go to that link, come on now. Oops. It's being possessed. Okay. There we go. Okay, so what are we going to plug in for our A value? Gracia.
What happened? Yes.
What are we gonna plug in for our A value? For the
Of
quadratic?
is ax2.
I see it's ax squared, but what are we gonna plug in down here from our formula?
I'm lost.
Okay? Were you paying attention?
Yes, I'm
honest?
just,
Are you
yes,
being
I'm paying
honest?
it.
Are you
Yes,
being
I'm
honest?
just, yes. It's
Are
just
you,
that
are you
my
really
eyes
now?
are so heavy.
Are you really now? Or do you have your telenovelas on and you're watching your televanilla? You're watching your soap operas.
It's just that my eyes are so heavy. Like I'm looking at the screen, but
Mhm.
my brain is not concentrating enough.
Okay. So I need you to concentrate, right? Guys, we only have a couple of weeks left. So we have this equation here. You see it at the very bottom that I'm bringing up to the top? Does
Yes.
this equation look like this equation up here?
It does.
Okay. So what would be my A for this equation in orange?
Your A would be 0.89 x to the square.
Okay. So
Root.
my A would just be that 0.89. So that's what we're going to be putting there.
Mhm.
Maybe. Okay. What about my B? What's going to be my B here?
Your B would be 0.0022x.
Okay. I actually made a typo. Was that right? Okay. Okay, and then my
Your C would be 0.0011. Is that a one?
okay. Okay, so I missed. Oh, I forgot our minus here. There you go.
Isn't it the coefficient for C is supposed to be negative?
Thank you. They're not. Yeah, you're right. Okay. So I have a typo in my last one. Okay, so we have two values. We have one that says we're going to have a negative amount that's being produced and one that says going to be a positive amount being produced. So then we have our X is going to equal the 0.0249
Why is it the positive one?
because you can't have a negative amount being generated. You know, you can
Oh,
remove
okay.
some, but you can't generate a negative. So if you already have 0, you can't go below 0.
Yeah, that makes sense.
Okay, so what we could have also done, we could have made an assumption that this value was so low that it's not going to have too much of an impact on here. If we had made that assumption, then we would end up with 0.100 molar over x squared. And then we would solve for x. So we get x squared is going to equal 0.0110, and x equals the square root of that. I'm having a hard time today. Oops, I forgot to square this. There we go. Okay, so by doing the quadratic formula the long way, we got 0.024. By doing it the shortcut way, it would be 0.0332. And so we know that in this case, this is like a third of that value. So we know that that would work for us. So we would actually have to use that quadratic formula to get the more correct one. Okay. When I did it this morning, I made a mistake with my calculations down there. So I have to correct it for the other class. Okay, so we know that this would be the molarity. This is how much being generated for our initial concentrations. Where is it? Okay, so all of our X values are going to be those values. And then our the equilibrium concentration for this guy is just going to be that 0.100 minus 249. So that's going to be 0.0751 molar. And then both of those are going to be the same value here. Okay, questions?
So it's the reactants minus the product to get the equilibrium?
Yeah.
For the molarity? Oh,
Yeah,
okay.
well, it really just depends on what's going on in the container that we're in, right? So here it's going to be the reactant minus the product, because that means that whatever's being removed is being delivered to the products.
Oh, okay, okay.
And so remember when we were talking about Le Chantelier's principle, about that shift, right?
Yeah, kind of.
So when we're talking about Le Chantelier's principle, you want to be thinking about Le Chantelier's principle all the time, because here we have only the product, we only have the reactant. So obviously we're going to be making product. But if we have products, right, that could affect, we could also affect, things could be going in the other direction. You know, so depending on Le Chantelier's principle. So.
Oh, so it depends where it's moving to?
That's right.
Oh, okay.
Okay, so here, calculate Kc with the initial concentration of 0.0150 molar of ammonia and 0.015 molar of oxygen gas with an equilibrium concentration of N2 equal 1.96 times 10 to the minus 3 molar. Okay, so what are we gonna do?
You're gonna find your givens.
Okay,
First,
so what are my givens?
So your givens is 0.0150 MH3 grams.
Okay.
And 0.0150 at the same MO2 grams.
Okay. Okay, so-
Concentration of N2 grams.
Okay, and that's equilibrium concentration, right? So I'm gonna have my ice table. So where am I gonna fill that stuff in?
Well, for the initial for ammonia, wouldn't you just put in the concentration for the ammonia?
Okay,
And the same thing with the oxygen and the nitrogen gas and the water. Wouldn't that be just 0
okay,
for the initial?
okay. So we have these factors here, right? So with these factors, we have to take in consideration what's going to be going on. So in this case, we have a 4, right? We have a 3, we have a 2, and we have a 6. So we have to take that in consideration when we're taking into account. So if we say that the change is going to be, in this case, 2x, so we're saying x represents just of whatever the factor is. And then this guy is going to be 6x. Then what's going to be removed here is going to be 3x. And then this guy is going to be minus 4x. Okay?
Mhm.
Oh, sorry, that's our equilibrium. Let me fix this. I got carried away. Okay, so in this case, as I said, this is going to be your 0.0150 minus 4x. This guy is going to be 0.015 molar minus 3x. Then this guy is going to be, we know the value for it already, it was given to us. It's going to be 1.96 times 10 to the minus 3. And then this guy is going to be 6x. Okay, so we already know what the 2x is. 2x is going to equal this value. So do we have the, can we solve for x?
Yeah, just divide by 2.
Okay. That's 8.8. Let me do the math before I make stuff up. So 9.8. Okay, so we have our values for x. We plug those in for all of our x values.
I mean, I would think so.
Okay, good.
Is that what you do?
That's exactly what you do.
Oh, okay.
Okay, and then you just solve for your concentrations here. So it's minus 0.015. So that's 0.0111 molar. So we have 3 times 9.8 So that's 0.0121 molar. We know what that one is, as it is. Then we have 6 times 9.8. E to the negative 4th times 6. And so that's 0.00588. So how would I calculate the equilibrium constant? Anyone?
I'm not sure if this is the reverse of what we just talked about, but I would think it would be just the reactants minus the products.
Would it
Are
be
you- Oh, you plug it in there?
yeah, because
Oh,
we're looking to solve the equilibrium constant, right? So then what would be this equation? What would be our equilibrium expression?
Would it be the products over reactants?
It's going to be the same thing. It's not going to change. It's going to be the products of the reactant. So it's going to be the concentration of N2 squared, concentration of water to the 6th power, concentration of ammonia to the 4th power, concentration of oxygen gas cubed. Okay. So if we plug in our values, Kc is going to equal 1.96 times 10 to the minus 3 squared times 0.0 0.0588 to the 6th power divided by 0.0111 molar to the to the 4th power and 0.0121 molar to the 3rd power.
and I got 5.90 times 10 to the negative 6.
Okay. Okay, good job. That's it. Not too hard.
Yeah. The first one looked harder, but that's only because there was an extra step involved.
Yeah. Okay. Everybody got this down? Okay, good. Okay. So use the following equation with an equilibrium constant Kp equals 0.11. to calculate the partial pressures of ammonia at equilibrium if 55.0 grams of ammonium hydrogen sulfide is placed in a 5.0 liter container. Okay, so we want to calculate the partial pressures of ammonia at equilibrium. We have our Kp. So what is it that we know about this? What's our givens?
Your equilibrium constant,
Okay, we
And-
have our equilibrium constant in pressure.
and you have your grams per liter to calculate the molarity. Or we would have to convert it to moles first.
Okay, so let's convert it to moles. So we have that 55.0 grams of NH4 HS. So what is the molar mass? Anyone?
Hold on, I gotta put out my calculator first.
Okay.
$51 grams.
Okay.
And I got 1.08 moles. Then
Okay.
you would just divide that by 5.00 liters to get the molarity for the initial concentration.
Okay.
And I got 0.216.
Okay. Okay, so now that we've got that, we have concentration, but we have Kp pressure. So what do I need to do to sit there and adjust the Kp pressure? And we also want to calculate the partial pressure, right? So is there something that I need to take care of to sit there and fix that problem? Can I use this concentration to get to the pressure?
The Kp or
Yep.
the initial one?
Although they're kind of,
Would you, and this is just a wild guess, but would you convert the KP to KC?
okay. And how will we go about doing that?
I know there's an equation, but I don't
Okay.
remember it.
You know, is this helping any? Because if you think about it, right? So our Kc and our Kp are going to be different because we have PV equals nRT, right? Equals nRT. We have our partial pressures is going to be equal to the molarity over RT, right? And so this guy's going to be dependent on the coefficients that we have. So in this case, this guy has, it's 1, 1, 1, right? So then you'll have RT, our products would be RT, RT divided by, or I should say RT squared minus, no, how do I say that? Products minus your reactant. So it'd just be RT. So Kc times RT is going to equal our Kp. Does that make sense? You remember that? Back. Beginning of the, hold on. Very, very beginning of the lecture. Kp equals RT delta N, where it's the difference between the number of coefficients for your reactants, your gas, I say your products minus your reactants. Yes, no, maybe?
Yeah.
Okay.
For last time, yeah.
Okay, good. Okay, so then if we have that, your initial was our concentration of, what's wrong? Question. Concentration of our ammonium Yep. And if we had a temperature, we could have actually calculated it here and we could just use Kp, right? I mean, if a temperature was given to us in the equation.
Yeah, because what did you need temperatures to convert it?
That's right.
AC?
Yep. So let's do for kicks and giggles, temperature is going to be 295 Kelvin. And so we could actually just change this guy to pressure, save us time because we want everything in partial pressure anyway, rather than having to change it to Kc, right? So if we assume that the temperature is 295. Then so we can plug that into this equation here. We have the concentration, which is, you said 0.0216 R, which is 0.0821 times, in this case, 295 Kelvin. And that's going to be our pressure.
I got 0.523.
ATM. Okay, so then we can plug that guy in as our starting pressure, our KP. Our KP, our pressure.
So you use the acronym ICE for pressure too,
Yep,
not just for concentration.
that's right. Okay, so in this case, we have the change being X. So this is going to be 0.525 minus X equal X and X for both of those. So then if we do our KP equation, KP is going to equal
The products divided by the reactants.
that's right, partial pressure of the products times the partial pressure of ammonia divided by the partial pressure of the reactants. So NH. Or HS. Okay, I'm gonna go ahead and move this, erase this. Okay, so we have our KPs, right? And KP is 0.110. That's gonna equal X squared over X. So, sorry, over, making a mistake here. 0.525 minus X. So then we get 0.11 times 0.525 minus X equals X squared. So we get 0.0576 minus 0.110x equals X squared. And so if we bring it so that we have the X squared with a positive value, so we'll bring these guys all over here, we'll get plus 0.110x minus 0.0576. And then we just use the quadratic equation. So this is the equation we're using right now. Oops. 1. 0.0576. Okay, so which value are we going to use and why?
D 0.191.
Okay. So X is going to equal 0.191 ATM. And so then we just plug that in. So we know that each of the, we want just for ammonia. So we have the value for the pressure of ammonia under those circumstances. Let's see. Okay, questions, concerns, Cash, Kool-Aid?
So you
Okay.
use the Dr. Henry.
Yep.
So you use the ice table for KP and KC.
Yep, you can use the ice table for KP and KC.
Okay.
Yeah, because we know that the concentration is always going to be proportional to gases, right? Based upon our PV equals nRT, right? So then we'll be able to sit there and do the ice table for that same concept. Okay. Let's see. Can I clear?
Yeah. Oh, for me, yes. I'm not sure about the rest of the class.
I know you
Anyone else? Everybody's good? Everybody
Yeah.
got it? Okay. Okay. Okay, it says, write the net ionic equation for the reaction of iron 3 nitrate with potassium thiocyanate to form thiocyanate iron complex ion. Calculate the equilibrium concentration for the reactants and the products with a Kc equal 1.10 times 10 to the third, diluted concentration of 0.0200 molar of the iron 3 nitrate and 0.00 molar of the potassium thiocyanate. Okay, so what are we going to do?
first write the equation.
Okay. So we have
Does nitrate have a -2 charge or -3?
nitrate has a -1 charge.
Oh, -1. Do you have to do the net ionic equation or just to figure out the balanced equation?
You'd have to, I would always start with the total ionic equation first. Well, you can get away with the net ionic equation, but it isn't going to make sense unless you have it totally balanced first. You know what I'm saying?
Yeah.
Okay.
Because I was just going to honestly try to just write that balanced equation.
Okay, so let's write the conventional balanced equation.
So it'd be FeNO3, and the nitrate would be have 3
Okay.
atoms.
3 compounds, yeah.
Oh yeah.
And
I don't know the chemical formula for thiocyanate though.
Anybody want to help her out? You have your polyatomic ion table? Mauricio?
Yes, I'm here.
Okay. Thiocyanate. What is the chemical formula for potassium thiocyanate?
It is. Wait, give me a moment. I thought I had it written down, but there's another one.
Okay.
Oh, I found it right here. It's SCN -1.
Okay, so potassium thiocyanate is going to be what?
Just KSEN.
Okay. And that's going to yield
The thiocyanate is gonna bond with the iron.
okay.
And then potassium nitrate.
Is it balanced?
No.
Okay, what do we need to do to balance it?
Well, you would need the 3 thiocyanate on the, yeah.
Okay. So it should be balanced now, right?
Yeah.
Okay. So then in this case, okay, so then our total ionic equation now is going to be F, or I'm sorry, the net ionic equation is going to be F E 3 plus what? Do you guys remember how to do it? What would be our total ionic equation first?
The total would be Fe3 plus potassium or nitrate, 1 egg, and then 3 potassium, 1 plus. Is that 3 thiocyanate, 1 egg? And wouldn't the thiocyano iron be solid?
It's not going to be a solid. It's actually going to form another ionic compound. So it's going to be Sb, Sc, and technically it's going to be 3 minus.
Oh.
I mean 3 plus, not 3 minus. 3 plus. Plus. Okay, so our spectators, So then we're just left with these guys. And electrons. Sorry, it's this. So at the end, you're making just your Fe, SCN. Two plus. And so this guy here is going to be an intermediate of this guy. So technically you're right, but this doesn't last long. Sorry, this guy doesn't last long. So you're right. So these are this is going to be basically your equation. And if we done this, right, based upon the concentrations, our net ionic equation is just going to be that Fe 3 plus your SCN minus yields Fe SCN 2 plus. Do you guys see it up in red up top?
Yeah, I could see it.
Okay, so if that's the case, if that's our equation, I'm going to go ahead and erase this part here. I need to put my aqueous. So it forms this complex, which is a little more stable for some reason. This guy is an aqueous, this guy's aqueous, and this guy is aqueous. Okay, so what are we going to start off with? What are going to be our givens for our ice table?
Well, you're given the initial concentration for both the reactants.
Okay, and so we know that for the iron 3 nitrate, this concentration is going to be good for the iron as well as for the nitrate, right?
Yeah.
Give or take, because the nitrate is going to be 3 times that, because there's for every 1 iron, we have 3 times the amount of that. So then in this case, our initial is going to be 0.0200 molar. Okay, what about the potassium thiocyanate? It's going to just be that 1.00 molar, because in this case, the potassium is going to be a total ion. So it's a 1-to-1 ratio with the potassium and the cyanate. So that concentration, that molar concentration is going to be the same. or it. Does that make sense?
Yeah.
Okay. And so initially we have 0 amounts of this, right? So our change is going to be x, x, x. So minus x here and positive x here. So equilibrium is going to be 0.0200 minus x, and it's 0.100 minus x. And then this guy is just going to be x. So then our Kc is going to equal. So what is going to be our expression, our equilibrium expression?
It's going to be x divided by.
Let's do it generically first. Concentration of what over what?
The iron.
Products of a
Or the
reactants.
cyanoiron.
That's right. So it's going to be our products of our reactants. So we have the cyanoiron, like you said, over
The thiocyanate and iron, or times iron.
okay, our iron and our thiocyanate. Okay.
Well, the charge, I see you're putting in. Are you just putting in to like represent it, or
Yeah,
is it
that's
going to
gonna
affect
present-
the?
It's not going to affect the concentration, right?
Oh.
Because it's the number of moles that you have of it is going to remain the same. The charge on the ion doesn't affect the number of moles you have.
Oh,
Does that
okay.
make sense?
Yeah.
Okay. So we plug in our concentrations that we know. So we have X divided by 0.0200 minus X times 0.100 minus X. And we know that that's going to equal our 1.10 times 10 to the third. Okay, so we plug in our values, or we solve for those values. So we have X equals 1.10 times 10 to the third times 0.0200 minus X. And I'm running out of room. Times 0.100 minus X. So we get X equals our FOIL method, right? So 0.0 0.0200 minus 0.100 X minus 0.020 X minus, oops, plus x squared times 1.10 times 10 to the third. So then we get 1.1 times 0.002. So we get x equals 2.20 minus 0.12 132x plus 1.10 times 10 to the third x squared. Seems so big. So we bring the x over here. So we get 2.20 minus 133x plus 1.10 times 10 to the third x squared. So if we plug those values into our equation, okay. Okay, so we had for our A, it's going to be 0, then e to the third. And then we have negative 133 for our B. And then for our C, it's going to be 2.20. Okay, so we have two values. Ooh. So if one case, if we use this 1.10 value, we know that that value would be too much. That would give us a negative value here. So we know that that can't be right. So the correct answer would have to be the second one. Does that make sense? Because if we use this value, then if we plugged it into this equation here, we would end up with a negative value.
Yeah. And you have to make sure the value is positive.
That's right. Okay, questions? Concerns? Cash? Kool-Aid? Okay, well, we'll stop here.
Are we gonna have a lab tonight?
Nope, all you guys, you can do it on your own. You don't need me to do it. You need to weigh your eggs in all of the 3 different eggs, record those weights, and then you are going to do the calculations for your osmotic pressure.
Oh, okay.
Okay. And you're going to be using albumin as going to be the majority of the content in your egg. Okay, does that help?
Yeah. I mean, I'm not sure how to find the osmotic pressure, but have you gone over it yet?
Yeah.
Oh.
Did
Maybe
I go over osmotic pressure, Mauricio?
I think we covered it in one slide.
Yep.
I'll check to make sure.
Okay. Okay, so on Wednesday, we're going to be going over chapters 14 and 15 pretty quick. So all it is, it's going to be the same type of thing. If you guys understand what you guys did today, you're in good standings. If you don't understand what you did today, you want to make sure that you understand it by Wednesday. So you want to look at the book and look at the notes to make sure you have a clear understanding. Okay?
Okay.
Okay.
Are we gonna have something about a group test, or is it just gonna be the final?
You're gonna have a handout. I'm working on it right now. So you guys, it's gonna be an open book, open notes, open group exam. You know. So, but the thing is that you guys can't copy off of each other. And then it's gonna be due the day that the final is due. So, does that make sense?
Yeah.
Okay.
And the final's still in person, right?
Yep, the final is still in person.
Oh, what day is that?
So you have the choice. You can come in. I'll send you the formal announcement here soon.
Yeah, because I gotta make sure I'm off work.
Okay, so you come in on the 26th or the 27th. And then I'll also be available on the 28th, but I'm gonna have a proctor for you on the. We have graduation that day.
Oh, okay.
So I prefer the 26th or the 27th. You have that choice. If you don't have a choice, we can do it on the 28th. And if I can't get a proctor because everybody wants to go to graduation, if I can't get a proctor, then we can make arrangements for it the 29th. But I have to have it by the. Okay.
So if we could go in the 26th or the 27th, I should be able to go in the 26th. That's a Wednesday.
Yep, that would be the best way. Okay.
And I'm assuming we'll have a written final and a lab final.
You are going to have a written final. You will have a lab final.
Was it the last one that we couldn't do when we went in person last time?
I'm waiting to find out if the chemicals come in. So I have to get some fresh chemicals for it.
Oh, okay.
Dr. Henry,
Yep.
I found one problem of osmotic pressure, but it isn't generally about osmotic pressure. It just includes some information about it.
Okay.
But I did find a nuclear.
Okay. Good. So that should be able to help you, right?
I'm assuming so.
Okay. Yes.
Chapter that one.
Yep. Yeah. Start there, and you know what chapter it's in, right? So. Okay. Any other questions?
I don't think so.
Okay. Okay. Well, then I'll see you guys on Wednesday. You guys have a good evening.
You too, Dr. Henry.
You guys actually will have one more lab left, and then I'll be working on it tonight. So I'll probably talk to you guys about it on Wednesday. It depends on, there's something else I have to do. It depends on if I get that done in time. If not Wednesday, it'll be that next week on that Monday. And so it'll be using the electrodes, and then also some of the clips, the LEDs.
Oh, okay.
Okay. See you guys later. Have a good day.
You too.
Bye-bye.
All right.
Bye-bye.
Bye, Dr. Henry. See you
Bye.
Wednesday.
I'll see you Wednesday. You have a good day.
Thank you. You too.
Bye-bye.